Work, Gary. Equation for work.
With the thing.
I'm sorry, I got a little lost there. Could you say that again?
F times GR, and in front of the F is the integral.
Ah, that would be the equation that's on your equation sheet. That's not the one we're going to start with. We're going to start with the one we used last year. We'll get to that one in just a little bit.
FT cosine theta.
FT cosine theta is the one we had last year. I'm going to use F delta R cosine theta rather than D delta R. This is the equation for the work with a constant force. Okay, so let us review some information about work. One of the basic things that you need to remember about work, Tyler, can I borrow your arm, please? One of the, a little bit, turn a little bit more, there you go. One of the things that you need to remember about work is a very basic concept, and that is this. It's a very important thing for you to get through your heads that the concept of work in physics is very different than the concept of work that you are used to. For example, class, right now, is Tyler doing any work? No.
It's just getting drained.
Now, it is important to understand that Tyler was not doing work. Vlad, why not?
It was moving, delta R was 0.
The displacement was 0. In order for work to occur, there needs to be a displacement. So work is F delta R cosine theta. Remember, work is always, we're talking about the work done by X force, okay? So in that particular case, that would be the force applied by Tyler. Now, while Tyler was unable to do work, please observe Mr. Palmer doing work on the book. Okay, so here we go. Class, please point in the direction of the force applied by Mr. Palmer. Please point in the direction of the displacement. Good. What's the angle between up and up? 0. What's cosine of 0? 1. So when I lift the book up, I'm doing positive work on the book. Okay, here we go. I'm going to lower the book. Please point in the direction of the displacement of the book. Please point in the direction of the force I apply to the book. Note that is up. What's the angle between up and down? What's the cosine of 180? -1. So notice when I'm lowering the book, I am doing negative work on the book. But when I lower the book, the force of gravity, please point, is down. The displacement is? The angle between down and down is? Cosine of 0? 1. So notice when I lower the book, the force of gravity does positive work on the book, but I do negative work on the book. So realize, whenever you're talking about work, you're always talking about the work done by whatever force you happen to be talking about. You have to specify what that force is. You could be talking about the net force, you could be talking about the force of friction, all sorts of different forces. One other example. Here I am walking at a constant velocity with the book. I'm going to change directions. Still walking at a constant velocity with the book. Please point in the direction of the displacement of the book. Please point in the direction of the force I'm applying to the book. So what is the angle between up and to your right?
90.
Cosine of 90 is?
0.
So how much work am I doing to the book? 0. So notice that the angle between the force and the displacement is key in figuring out what type of work you have here, whether it's positive or negative. The dimensions for work, Sierra?
It's joule.
It is a joule. What is a joule, Sierra?
It's a Newton.
Newton times a meter, called a Newton meter. Good. We have so far work. So the way this is defined actually is using the dot product, which is also called the scalar product. And that is work is equal to F dot delta R, any dot product. Let's see. So let's just go and talk about a little bit of, talk about it in terms of math here. A dot B is equal to AB cosine theta. So this is actually a figure from your text, and it does a very good job of describing what the dot product is, what the scalar product is. We have vector A and vector B, and A dot B, the scalar product of A and B, is AB cosine theta, or it's multiplying A by the projection of B on A. So that is what the scalar product is, and it's an important thing to keep track of and remember when you're doing the scalar product. And we'll go through some examples of doing the scalar product today. That gives just a good visual of what the scalar product is. All right, so let's just do some basic math here. We've got vector A is equal to 4I plus 3j plus 0k. And if vector B is equal to negative 2I plus 4k, or plus 4, plus 0j plus 4k. The vector product, or scalar product, A dot B is equal to what? To remind ourselves how to do this with unit vectors. Remember how to do it with unit vectors. You've seen this before, yes? True statement? Yes, Mr. Palmer, I've done this in my math class. This is, remember, this is AP Physics where we take a lot of math that you've done before and we give it purpose. Hamza?
You do 4I times negative 2I.
Actually, it's just 4 times negative 2. Because it's the scalar product. That's a key term here. So we actually end up dropping the direction. Okay, keep going.
Plus 3 times 0. Plus 4 times 0.
I'll do 0 times 4, but yeah, just to keep the same. So this is equal to negative 8. Now we didn't have dimensions, I was just going through a basic example. That's how you do this using unit vectors, I, J, K.